Hey everyone, welcome back. So in this video, we're going to be talking about the SIR model in epidemiology. So this model has unfortunately been at the forefront of a lot of research lately because of the coronavirus pandemic and a lot of very brilliant scientists trying to understand the dynamics of this pandemic. So this is the base model on which all more complex, more intricate models in epidemiology are typically built. So it's very important we understand the dynamics of this model so you can go ahead and see how to extend it for your own needs. So the SIR model is what's called a compartmental model, which just means that it assumes that there's a population of people, and each of these people lives in one of a couple of different compartments, either the S, the I, or the R. Now, before I get into those compartments and what they mean, it's important to note that the base SIR model assumes that there's N people in the population, and this N is fixed throughout all time. So there's no entrances, there's no exits from the population. This may or may not be a good assumption for the population you're looking at. Now, the three compartments that the SIR model says that you live in one of them is either susceptible, which is the S in SIR. This is people who have never had the infectious disease, but who may get it in the future from a currently infected person, which brings us to our second category, infected. These are people who currently carry the disease and are able to actively infect other people. And our final category is recovered. So these are people who once had the disease in the past, so they were once infected, but have since recovered and they're never going to get the disease again. So a couple things to note here. First, notice the flow of people through this diagram. If you're susceptible, the only potential different place you could go in the future is infected. If you're infected, the only potential future place you could go is recovered. And if you're recovered, there's nowhere to go. You'll notice there's no arrows coming out of this box, which means once you're recovered, you're just in that category forever. Now, based on everything I've said, you may be kind of nodding your head and saying, I'm not sure if some of those assumptions are true. And you're right. This, again, is the base model. So there's a bunch of assumptions built in. And the truth is that most of them are not going to be completely valid for whatever case study you're looking at. Just to name a few, there's many diseases where even if you recover, you could get it at some point in the future. Just to name another one, this has no kind of intuition of a vaccination. So people in the vaccine category where you don't have the disease and you'll never get it because you're vaccinated. So there's a lot of assumptions to think about here. But assuming that we understand the basic flow of the model, let's move on. This model basically says that as time goes on, the number of people in these compartments changes based on interactions between people in various compartments. So to give a little bit of a real example, consider a small population of just 6 people. 4 of them, let's say, are susceptible to the disease. 2 of them, let's say, are currently infected with the disease, and let's just say nobody is recovered right now. Now let's think about the various interactions and what could happen. One thing that could happen is on a given day, or actually more like an hour, so a small time window. Let's say that a susceptible person interacts with another susceptible person, so shakes their hand or talks to them in public or something like that. Now, if it's a susceptible interacting with another susceptible person, nothing's going to happen. Same thing if an infected person interacts with another infected person, nothing's going to happen. But things get different when you think about a susceptible person interacting with an infected person. Now, although it's not guaranteed that the disease is going to be passed on, now there is a chance of the disease getting passed on. And we'll be modeling that transmission chance or propensity shortly. So now that we understand the various compartments, the various assumptions, and how the disease spreads through the population over time, let's go ahead and only now look at the mathematics behind the model. So the mathematics behind the model are fully governed by these 3 differential equations, ds dt, di dt, and dr dt. And these basically just say what's the change in the quantity, for example, S, at a particular point in time. So if this quantity is very, very high in absolute value, that would mean that the number of susceptible people is going down very fast, which means that they're going to the infected compartment, because that's the only place for them to go. So that means the disease is getting transmitted very fast in this time window. If this is very small in absolute value, then it's better news, because that means that there's not a lot of people getting infected in this small time window. So let's go ahead and break down the story behind this equation, because although it looks a little complex, looks like there's a lot of variables here, each of them tells a small piece of the story, and once we tell the entire story, it's going to be pretty clear what ds dt is. And furthermore, it makes our understanding of the other 2 differential equations pretty easy once we understand this one. So let's go ahead and get started with the story. Let's look at this first component. So I over n. I is the number of infected people, the current number of infected people. So really what I should have written is I parentheses t, because know that the infected people is a function of time. but I just, for simplicity, wrote just I, just S, so, but implicitly know that this is I of t, this is S of t. So I over n is the fraction of currently infected people, right? Because n is the number of people in the population. I of t, is the number of infected people right now, so I divided by n is the proportion of infected people. To be concrete, in our example here, I is 2, and the number of people is 6, so 2 over 6 would be 1/3. So that would be 1/3 here. What does this mean? This means that if I am currently a susceptible person, then there's a 1/3 chance on any given small time window that if I interact with somebody at random in the population, it's going to be an infected person, right? Because if I'm this susceptible person right here, then if you think about how many people in the population, there's 6. If I interact with one of them randomly during a small time window, then there's a 2 out of 6 or 1/3 chance I'll be interacting with an infected person. So that's the beginning of our story. Now we get this parameter called beta. So this beta is called the act rate. And basically what it says is how many interactions do I have in a small time window, whether that's a minute or an hour or whatever we're considering here. So this plays very well with the previous measure that we just looked at, because the first measure looked at if I'm interacting with a random person right now, what's the probability that they're infected with the disease? And beta is saying how many of these interactions am I having in a small time window? So it's basically just scaling up this probability I looked at back here. Now the other parameter that we're looking at here is called tau, and tau is called the transmission propensity. So it's basically a measure of if I am currently talking or interacting with an infected person, what is the propensity for them to pass the disease to me? So the higher tau is, that means that this interaction is more likely to result in me getting infected. The lower tau is means that even if I am interacting with an infected person, there's not as high of a chance that I'll actually end up with the disease afterwards. So far, these three quantities are telling the story that what's the probability that I'm interacting with an infected person? How many of these interactions am I having in the small time window? Multiply that by if I am having an interaction with an infected person, what's the propensity for me to actually get the disease from that? Okay, and there's one last part of the story, because everything we said so far was just for a single susceptible, but we know that there's many susceptibles at this current time point. How many are there? Exactly S, or more concretely, S of t. So we basically multiply the entire story we just told, which was for one susceptible, by S, so that we can see what's the change in the number of total susceptibles at this current point in time. Okay? So hopefully that story made this equation a little bit easier to digest. Again, there's 4 pieces, and each of them tells a very concrete part of the story. The last thing I'll say is that there's a negative sign in the front, because if you think about the quantity S, the number of susceptibles, it can only go down over time, right? Because the only place they can go is infected, and notice there's no arrows leading into this bucket, so of course the number of susceptibles has to be only decreasing. And since each of these quantities we looked at is positive, we just put a negative sign in the front, so that the derivative is always negative, okay? So, truth be told, that was the hardest one to understand. Now, the other 2 differential equations are going to flow really well. Let's look at actually DRDT next. You'll notice it's a much simpler form. The story is much easier to tell. DRDT is the change in the number of recovered people over time. And we're basically just simply saying that it is equal to subparameter gamma, which we call the recovery rate, times the current number of infected people. So this is I of t. So we're saying that if I of t is higher, then the change in the number of recovered people is also going to be higher. Another way for DRDT to be higher is if this base parameter, the recovery rate gamma, was also higher. Okay? So that is the story being told here. Now, actually, why are we done? Why don't we have to say much about DiDT? Because there's a very crucial assumption we said in the beginning, which is that the number of people in the population is fixed for all time. What does that imply if I were to add dsdt plus DiDT plus DRDT? They have to add up to 0. The reason is that each of these says that what's the change in the number of people in that category over time. And since there's n people in the population, the total population has a derivative of 0 at any point in time because it's not changing, not growing, not shrinking, which means that if we add up the categories' derivatives, they also have to add up to 0. So that means, or basically forces, DiDT to be a quantity such that the sum of this guy, and this guy is 0. And since we already have these 2 guys, we can pretty easily just plug in the quantities and get the equation for DiDT. So you'll notice it's just the equation for dsdt without the minus sign minus the equation for drdt. Okay? So now that we understand these differential equations, what each of the parameters means and how we derive them, let's go ahead and look at an actual graph. And now we'll throw in some terms that you may have heard in the media a lot throughout this crisis, such as flattening the curve. What is the curve we're flattening? We'll also talk about a very important quantity called R0, which you may have read in some articles. So what I've drawn here is the beginnings of the S, I, and R curves over time. So as the disease progresses throughout time and spreads to people in the population. What are these curves typically going to look like? So we have that this axis is time, and we have that this axis is just number of people in any of the categories. So for example, the green curve here, which is the number of susceptible people, will start at some value S0. So that's typically most of the population. So that's why the red curve, the number of infected people, starts at a very low value. And of course, at the very beginning, nobody is recovered because nobody really has the infection to begin with. So now let's just look at these equations and see what might be happening to the disease over time. Let's first look at dsdt. So dsdt, the only two dynamic factors that are actually changing are I and S. Everything else in here is a fixed parameter. So in the beginning, I is very low and S is pretty high. So this thing is not going to be super high in the beginning, which is why you see that there's a very slow decrease, at least in the beginning. But whatever decrease there is implies that these people are going from susceptible to infected. So that's why the I curve, the red infected curve, is growing in the beginning. And as the red infected curve grows, drdt also gets bigger because I is a direct factor here. So that's why the blue recovered curve also starts growing. Now the important observation about what's going to happen in the future comes from looking at this didt equation. Notice that we can do one crucial thing, which is factor out this I, since it lives in both of these terms. So what I've done here is factored out the I. It got a little bit messy, but here's the I right here, and then here's the other terms. Now let's think about when didt is equal to 0. When is that curve going to be at its maximum? So that's going to be exactly when this inner term is equal to 0. Now this inner term, there's only one thing that's really changing over time in this inner term, and that's S. If you look at everything else inside the inner term, it's a parameter, so it's not going to be changing. And as we said, S starts very high, up here at S0, and it's always decreasing over time. So there's going to be some point at which this first term gets small enough where it's actually equal to the second term, and at that point we're going to have didt be 0. What does that mean graphically? That means at some point in the progression of this disease through time, the curve is going to reach its maximum, and by the curve I mean the infected curve. So we see that although it's increasing, at some point it's going to reach a peak, and then it's going to start going down after that. Now that we see what that curve looks like, we can actually see what the other curves are going to look like as well. Because that means that the susceptible curve is going to be decreasing very quickly at first, and then is basically going to be tailing off. The reason it's going to be tailing off is because if we look at the red infected curve again, we see that around this area, there's a lot of infections at each period in time, which means that the number of susceptible people is going down very quickly. But as the red infected curve kind of tails off, and there's less infected people at each point in time, which also means that the number of recovered people is going up, that means the green susceptible curve will be tailing off. So this is what a typical SIR curve diagram looks like. Now the media focuses a lot on only one of these curves, and for good reason. So we typically focus a lot only on this red infected curve because it tells us the story of at any point in time, how many people are currently infected. Why does that matter? And why is that the curve that we're trying to flatten? To think about why we need to flatten that curve for the good of the entire society, think about what would happen if I drew a very steep infected curve. So instead of this infected curve, think about looking at something that looked like this. So although the previous infected curve and the new infected curve I drew both may have the same total number of infections over time, there's one big, huge issue with the new infected curve I drew, which is that around this area, there's a ton of people all infected with the disease at the same time. This is problematic because the hospital may not be able to keep up with that number of people. We may not have enough ventilators, may not have enough masks, may not have enough whatever medical equipment that we need to handle that spike, that number of infections all at the same time. versus if the curve was flatter, or even flatter, maybe something like this, which didn't get drawn very well, but even flatter, that would mean that although the infection lasts longer, so you'll see that the tail is heavier, there's not so many people infected at any one point in time where the hospital can't handle that number of people. So that's why it's very important and what we mean by flattening the curve. Now that we know graphically what it means to flatten the curve, how do we actually flatten the curve? What can we do as a society? And why are these things helpful? And what do they mean in terms of the model? To see that, let's finish this video by looking at a very important quantity in infectious disease modeling called R0. So R0 is basically a measure of how problematic is the disease for the population. So that's kind of the umbrella explanation. But more specifically, it is if you have the disease, what is the average number of people that you're going to pass the disease on to before you no longer have the disease? How would we calculate that? Well, before we calculate that, let's reframe some of our parameters in terms of different physical quantities. First, looking at beta. We know that beta is the number of interactions per time. So if our small time period is like a minute or an hour, we know beta is the number of interactions you're having with other human beings in a minute or an hour. What does that mean for 1 over beta? That would just be flipping that intuition. So that would be the average time between interactions. So just to put a number on it, let's say that that is 2 days. So this just says that, let's say that every 2 days you're having an interaction with a different person. Now we can use a similar chain of reasoning to say that 1 over gamma, since gamma is the recovery rate, 1 over gamma would be the average time to recovery, which means that if I get the disease right now, what is the average number of days until I no longer have the disease? And again, to put a number on it, let's just say this is 10. So let's say this is 10 days. The reason we did this is now if you think about these two things and how they interact with each other, let's say I have the disease for 10 days. So let's say I get it today and 10 days later I no longer have it. I also know that every 2 days I'm having an interaction with someone. That means that there's 5 chances, 10 divided by 2, 5 interactions where I'm actively able to pass the disease on to somebody else. Now that doesn't mean they're going to get it because there's another parameter called tau, the transmission propensity, which governs what's the likelihood that if I do have an interaction and I'm infected, what's the probability they're actually going to get the disease too. So let's put all these together to build the metric known as R0. So first we're going to, as we did, 10 divided by 2, which would be like doing 1 over gamma over 1 over beta. So 1 over gamma over 1 over beta. So that's the number of interactions I have where I could pass the disease on, but I have to multiply that by the transmission propensity, because that would be the likelihood that they actually do get the disease from that interaction. So times tau, and this is equal to beta tau over gamma. And this is the quantity called R0 in terms of the parameters of the model that we already defined. So if we want R0 to be lower, because that's what we always want for an infectious disease, is to get R0 as low as possible, then there's basically 3 steps we can take. Either we decrease beta, we decrease tau, or we increase gamma. And just to close this video, what does doing these things mean in terms of real-world actions? So let's go through one example of each. Beta, as we said, was the act rate, the number of interactions you're having with people in a small time window. Decreasing the act rate would be something like social distancing, which basically means that if you're more distant from people, that would mean that the number of interactions you're having with them is going to naturally be lower. Another thing that governments did to decrease beta was to close crowded spaces like schools and movie theaters, because now there's going to be less interactions between strangers at any given time period. What does it mean to decrease tau? Tau is the transmission propensity, which again means that if I am interacting with an infected person, I want to decrease the risk or chance that the disease will actually be passed on. This would be something like governments enforcing you to wear a mask, a face mask, because that means that even if I'm interacting with someone who does have the disease, but we're both wearing face masks, then the chance of transmission is now lower. So that's what an intervention with tau would mean. And what about gamma? Gamma, remember, is the recovery rate, and we want to increase the recovery rate, which would be the same thing as decreasing the time to recovery. So I'm not a medical expert by any means, but I know that for many diseases, you can actually expedite your time to recovery by doing stuff like taking proper bed rest, taking proper medications, drinking lots of fluids, and things like that. So those would be interactions that you could do to yourself that would cause the time to recovery to be lower, and therefore gamma to be higher. So this was in a nutshell, explanation of the SIR, the susceptible, infected, recovered model in epidemiological modeling. And all kind of models that are more complex, more realistic, are kind of based on this groundwork. Because now you can think about extending this model. What if we had a category for vaccinated people? What if we assumed that you could get the disease again after you had gotten it once? This is all kind of extensions of this basic framework. All right, so I hope you learned something in this video. If you have any comments at all, please just leave them below. And please like and subscribe for more videos just like this. I'll see you next time.